do it. So with that being said, let's go ahead and look at what we're doing today. So we are going to be looking at limits intuitively. I will say this is the one where, how can I say, it's usually students' least favorite way to do limits because it is just like, usually there's no work, which you're like, oh, great, no work, but that also means there's just like a lot of like thinking and conceptual and theoretical stuff going on. But limits intuitively. Before I get started with limits intuitively, I do know there's probably some prerequisites that I want to review. And those prerequisites deal with the exponential graph and the natural log graph. And so hopefully you know these. If not, we're going to kind of review them real quick. We know we have e to the x and the natural log of x. I'm going to do e to the x first. E to the x is your basic exponential graph. It does have a horizontal asymptote at y is equal to 0, and without any transformations, it's crossing at 0, 1, and it's an increasing function. And you might be asking yourself, Mr. Brown, why are you showing us this? And my short answer is like, just wait till what's to come. But then also just like a lot of these intuitive limits, you just have to have a good feeling for what the functions look like. The natural log graph, which is the inverse of e to the x, instead has a vertical asymptote instead of a horizontal one. Its vertical asymptote is at x is equal to 0. And since it's the inverse, instead of crossing at 0, 1, it's crossing at 1, 0. So I did want to answer kind of these limit questions just to kind of mix in some calculus with these prerequisite skills. Remember, if you can plug it into the function, always plug it in. So like for e to the x, if x is going to 0, we can plug that in. And e to the 0th power is just going to give you 1. The limit as x goes to infinity would be d and e, because that graph is always growing as x goes to infinity. And then the limit as x goes back to negative infinity is equal to 0, because we do have a horizontal asymptote at 0. On the quiz, most people are really good at identifying the limits from a graph, which is great. Now for the natural log. I'm going to do the easy parts of the natural log first. We have the limit as x goes to infinity, and the limit as x goes to infinity is going to still be d and e. This graph is increasing forever, so it is going to be d and e. I did want to talk about the other two because they're kind of special cases for the natural log. So the first one, I'm actually going to do the negative infinity first. Technically saying x goes to negative infinity doesn't really make sense for this problem. Like the technical answer would be does not exist, but it's really just best, like I wouldn't ask you like what is x to negative infinity, because the graph is always greater than 0. So that does bring me to this first one. Your prereq skill that I hope you remember is that the natural log of 0 is undefined. Like that is something that is true. You should know that from Algebra 2. If not, I'm telling you now. But the natural log of 0 is undefined. But for this one, I did go ahead and say, what is the limit as x goes to 0 from the right? Because that does have a different answer. It is undefined, but we're going to think about it a little bit differently. So as x goes to 0 from the right-hand side, the graph is approaching a vertical asymptote, but always going down. So it is going to be d and e, but it's because the graph is headed towards negative infinity. That seems like a weird distinction to make, but we'll again see that a little bit later in class for what I mean by that. Any questions about those reminders?
No.
All right, so next part I want to look at is going to be this flow chart to remind you of. So we did this flow chart before the quiz. Probably been a while since you had it pulled out. Maybe you can find it in your notes. But we know that when we're finding a limit, we often want to find, do direct substitution first. If you get a real number, that's your answer. If you get a number over 0, your limit automatically does not exist. And then if you have 0 over 0 or infinity over infinity, the one that we talked about was their algebra skills with like factor cancel, rationalize, and then like common denominator or anything else. I'm going to add another case. And this is not a math term by any means. It's just something, an acronym used to help you memorize your answers. It is going to be used when you have 0 over 0 or infinity over infinity. In fact, usually you're going to have something like infinity over infinity. And I call it FEPL, F-E-P-L-E. And it's going to be useful as x goes to infinity. So then you're like, well, Mr. Brown, what does FEPL represent? And so this is a strategy that I use for problems when x is going to infinity, and it's a little bit more difficult to kind of figure out what it's going to be. And FEPL stands for 4 types of functions. The 4 functions we have, F stands for factorial, E stands for exponential, P stands for power or polynomial, and L stands for logarithmic. Factorials in math are any time you see the exclamation mark. Before you get too worried and you're like, Mr. Brown, I've never seen a factorial function, we're not going to sweat it. Because actually factorials, those are only going to be shown in BC. So I guess I could have taught AB and just said we're using the EPL method, but I just used the same notes from BC. Factorial is something you won't ever see in this class. Exponentials you will. Remember for exponentials, those are examples where the x is in the exponent. So there's some examples. Whenever you see x in the exponent, you have an exponential. Power or polynomial is when you see the x as the base and a number is in the exponent. And then, of course, logarithmic could be anything from like a natural log to a log of any base. And so you might ask yourself, well, okay, so I know those functions. We have exponentials, power, and logarithms. And FEPL helps me remind myself the order of kind of extremes for them. And what I mean by that is what comes first is going to have the fastest growth. And what comes at the bottom is going to have the slowest growth. Notice that none of those are like not growing. They're all kind of growing. You're just kind of saying which one's growing the fastest. So now we're going to drift into like some theoretical land. So go ahead and put like your biggest thinking cap on so I can kind of describe what we're going to be heading towards for this lesson. When I say infinity in math, what do I mean by infinity?
A number that keeps increasing and increasing.
A number that keeps increasing, right? Can you ever technically reach infinity?
No.
No.
No, it is just like an idea. It is like the biggest number that just keeps going and going and going. Well, in math, and this is about to sound like a crazy statement, in math, we have this idea that some infinities are bigger than other infinities. And you're like, but wait, Mr. Brown, infinity means you go on forever. Yes, we're still going on forever, but some kind of go on forever a little bit faster than others, so they end up being a bigger infinity than others. Think about it in terms of money. Do you want to have your money increase exponentially or just logarithmically? I'll choose exponentially because that's a much steeper graph. I'm going to have a lot more money at the end of the day if that's my goal. So when we're talking about FEPL, we're going to think about what's the fastest growth to what's the slowest growth. And so to put this into context, it's going to be useful when we're making decisions that look like this. And I'll give you a chance to write those down if you need them. I have them boxed. I'm trying to group like the red ones kind of go together as the same function. The blue one does not go, those all go together. Some of these use this method called FEPL. Some of them are going to just be direct sub, and some just might be some other stuff we need to think of. And so when we think of a problem like this, we often need to kind of think about, okay, so we're going towards infinity. We just talked about how like infinity is a number we can't reach, so you can't like actually plug in infinity. That doesn't make sense mathematically. But we just want to think about what's happening when we do a problem like this. And so when I'm looking at these problems, let's look at this first one. I have the limit as x goes to infinity of x squared over e to the x. Now, if you're like me, you have no idea what that graph looks like. It's something that I just completely made up. So let's kind of think about this piece by piece. So x is going to infinity. Let's just think about the numerator right now. If x is going to infinity and I have x squared, well, visually, what is infinity squared still going to be?
Infinity.
Infinity, right? If you're already going out forever, if you square it, guess what? You're still going out forever. Now let's think about e to the x, plugging in infinity into our heads. So we have e to the infinitieth power. Well, if we're already going to infinity, what is e to the infinity still going to be?
Infinity.
Infinity.
Infinity. You're still going out forever and ever. So the case we have here is technically the case of infinity over infinity. But that's not really the answer. We know when we see that we really need to keep going, that's called one of the indeterminate forms. And this is where FEPL is going to help us out. X squared, how would we classify x squared of FEPL? Would it be the f, the e, the p, or the l?
The P.
The p. It's a polynomial. X to the base number is in the exponent. And then e to the x is kind of clearly the exponential one. Which one of those is the bigger infinity, the polynomial one or the exponential one?
Exponential.
Polynomial.
Exponential. So remember, we have FEPL. We won't really see f in this class. E, P, L. E is much, much larger than the numerator. So in my head, when I'm thinking, okay, so this is going to infinity, but the denominator is so much more bigger than the numerator. So I need to think about where this fraction is going overall. So again, this is all kind of in our heads. We'll get more used to this as the notes go on. But if I have these fractions up here, I'm going to think about 1/2, 1/10, 1 over 1,000, and 1 over 100,000. Which one of those fractions represents the smallest number?
The last one.
The last one. It's getting close to 0, right? So like 1/2 we know is 0.5, 1/10 is 0.1, and then we just kind of keep adding zeros into the problem. So we're getting closer and closer to 0. So in our heads we're thinking, so we have two infinities, but it's bottom heavy. So we basically have a fraction with like a small numerator and a really, really, really big denominator. What will be your guess that this limit is going to go towards as x goes to infinity?
Negative or like 1?
Let me ask it a little bit better. So if I just have a fraction and I have, I'll just stick with a random number, 5 up here and 10, I know that's 0.5. But if I keep letting that denominator get bigger and bigger and bigger, what decimal is this getting closer and closer and closer to?
0.
0.
0. So like as we keep getting the denominator bigger, so that's basically what's happening in this case. The denominator keeps getting bigger and bigger and bigger and bigger. So overall, this fraction is eventually going to approach what value?
0.
Same thing that the other fraction was. It's going to approach 0. So the limit for this problem is simply just going to be 0. Heavy infinity on the bottom, your limit is going to go towards 0. So let's go ahead and try the one next to it in the blue column. Let's see how this is working for us. So I'm saying that x is going towards infinity, and I have x squared over the natural log of x. We don't know what that graph looks like. We can't really plug in infinity. It doesn't make sense, but we can use FETFL. X squared is a polynomial, and natural log is, of course, the logarithmic. In that fraction, which one's going to have the bigger infinity, x squared or natural log of x?
X squared.
X squared, so we have the bigger number up top, the smaller one on the bottom. Again, they're both pretty big. They're both infinity, but one is a whole lot bigger than the other. So for this one in my head, I'm thinking of a fraction where the denominator is bigger, and it just keeps growing faster and faster than the denominator can. If my numerator gets really, really large, where is that fraction going towards overall?
Infinity.
Infinity.
Infinity. So it is going towards infinity overall. If it's going towards infinity overall, can we say the limit is?
Infinity.
Infinity.
Infinity. So if I want to summarize those two cases, bigger infinity on the bottom. So we have the bigger infinity in the denominator, your answer is going to be 0. If you have the bigger infinity in the numerator, then your answer is going to be does not exist. Now, of course, you know this is calculus. It's not always going to stay that straightforward. So I did kind of put on here some other strange cases. So in this next one in the red column, I have the limit as x goes to negative infinity of x squared over e to the x. So let's imagine, again, we can't really plug in negative infinity. So I'm going to write some stuff down, but it's really what's kind of happening inside my head. I'm going to plug it in, and I have this negative infinity squared over e to the negative infinity. And you're like, that makes no sense. And I'll be like, yeah, that makes no sense to me either. But let's think of kind of what's happening here. If you have a really, really, really big negative number and you square it, what is it still going to be? Or what is it going to be?
Positive infinity.
Positive infinity. So that's going to become positive infinity. And then negative exponents, for limits, negative exponents are really hard to deal with. What can I do to get rid of that negative exponent? Think about your properties of exponents.
The reciprocal.
The reciprocal, right? So like if I have 1 over 3 to the negative 2, that's the same thing as just saying 3 squared. So this e to the negative infinity, I can just move up and think, oh, that's just times e to the infinity. So I can get rid of that negative by doing the reciprocal of it. So again, this is all kind of in my head. Well, if I have an infinity times e to the infinity, what number is that still going to give me? It's still a big number, it's still infinity. If
Infinity.
the answer is infinity, then the limit would be does not exist. And I know some of you are stressed out right now because you're like, Mr. Brown, we're just talking about like multiplying infinities and it still is infinity and I have no idea what's going on. I promise you, you will, but like, yeah, these limits intuitively are kind of weird like this. Like we just have to kind of think through them and think what it's going to be using our knowledge of like how big numbers and little numbers and negative numbers kind of all interact together. So let's try this next one. I have the limit as x goes to 0 from the right. So I'm going to x to 0 from the right. So basically as close to 0 as you can get from the right-hand side. 0 from the right of x squared is going to go to what value? Or I'll even say it this way, if you're just going for as x goes to 0 of x squared, what's that going to go? Just going to be 0, right? We can say, okay, that's still going to be a very small number squared, so that's going to be 0. About 2 slides ago, I told you what we're going to think about the natural log of x's from 0 from the right. For this class, how do we define the limit as x goes to 0 from the right of the natural log of x?
Undefined.
It is undefined, but how do we think of where it's going?
Going towards negative infinity.
Going towards negative infinity. So this fraction is technically 0 over a negative infinity. And you're like, Mr. Brown, that doesn't really make sense. So again, here's where the intuitive part comes into play. If I'm coming in from 0 from the right, that's better thought of as just vaguely as a very small number squared. Because like 0 from the right would be immediately to the right of 0, so like 0.00000001. So I basically have a very small number over infinity. Well, if I have an infinity in the denominator and a number up top, where would this fraction be going towards overall? So you have some
0.
number, you're dividing it by the biggest number you can think of. What would that fraction be equal to?
0.
0.
0. So again, big infinity on the bottom, that limit is actually going towards 0. And then these last two, I put these on here just to make sure we can do the easy ones and also to make you not feel as dumb if you're a little bit stressed out right now. Don't be, but these should be two easy ones. Remember, if you're just going to a number, it's just easy enough to plug it in directly. So that first one, plugging in 1, 1 squared is 1, e to the first power is just e. The second one, plugging in e, I have e squared over the natural log of e. You can reduce that. The natural log of e is just 1, so you can write your answer as e squared. And so that's how notes are kind of going to work for today and tomorrow. Like there's going to be just like a lot of thinking, a lot of like dealing with this concept of infinity. I do want to make sure I give us the necessary practice so that we feel comfortable doing all of this. So I know it's going to seem weird that I'm introducing another topic right now, still limits, but kind of it's helpful to talk about FEPL when I have something else. And another method that we have when we're dealing with infinity over infinity. So FEPL is of course useful. I also have another one that I represent as WMM, and it stands for what matters most. And this one is often used along with FEPL at the same time. So I want to go ahead and introduce this one because we'll be looking at both FEPL and what matters most. And what matters most is going to be nice because it's going to work for both positive and negative infinity. So to give you an example with what matters most is I want to go back, let's forget about e and natural log and crazy functions. Let's go back and deal with rational expressions. And so I have two of them on here. I have one as x goes to infinity, and I have another one as x goes to 2. And I chose the same function for a reason, but looking at both of those, which one of those do you already know how to do?
The second one.
The second one. We know when we have a number, we can always try direct substitution. So like 2 squared minus 6 plus 2. So that's going to be 4 minus 6 plus 2, we get 0. And then I have 2 times 4 minus 8 is 0. We're a little bit annoyed, but we all know how to do that one. How do I need to finish up that problem?
Factor the
Factor and cancel. So these are the ones we've been doing. So I'm just going to go ahead and kind of do it quickly. So I have x minus 2, x minus 1. Factor out a 2, and that gives me x squared minus 4. So 2x plus 2, x minus 2. The x minus 2's are going to cancel each other out. We have a nicer limit to deal with, and I can go ahead and plug in 2 into what's left over. And that's a 1. And so plugging it in, we see we get a number now. 2 minus 1 is 1. 2 times 2 plus 2 is 8. So we know how to do those. When you have a number, don't do things like what matters most or FEPL or things like that. When you are going to an infinity, these are the ones where you can't really like factor and cancel. Like it doesn't make sense to do that. And so I want us to look at this top one that is a limit as x goes to 1. And for me, this will be an example of what matters most. And so let's think about in terms of infinity again. For this, let's talk about money. Money is an easy way to conceptualize and think about it. And we're going to think about Jeff Bezos. Owner, founder, Amazon, has way more money than he ever needs, but he has a whole lot of money. So imagine you're Jeff Bezos and you just have billions and billions of dollars, and you're walking around and you drop $10. Are you going to miss those $10?
No.
No.
No, like you just have so much money, like $10 is nothing compared to what you have. And that's kind of how what matters most works like. To put it more in a math concept, if I have infinity and take 2 away from infinity, how much do I still have?
Infinity.
Infinity.
Infinity, right? If you're already going out forever and you take away 2, well, guess what? You're still going out forever. We haven't changed the problem. So what matters most is helpful if you have more than one term. And please only use it when you're going towards infinity or negative infinity. It does not work if you're going to like 2. You still need to like factor and cancel and do all of that. So how this one will work at infinity is you kind of ask yourself is, well, as x goes to infinity, what is going to matter most? What's the most important term? So looking in that numerator, we have x squared, a negative 3x, and a 2. At infinity, what is going to be the most important term of that numerator?
X squared.
X squared. And the way you kind of reason that is, okay, so if you square a number, it gets really big. If you square infinity, it's obscenely big. Negative 3x, yeah, that's a huge number, but not as big as x squared, especially in terms of infinity. And then like that plus 2, doesn't even matter. It's just plus 2 and you're already at infinity. So that x squared is what matters most. Looking in that denominator, what would you say matters most?
The 2x squared.
2x squared, right? That minus 8 doesn't matter at infinity. And so what happens with what matters most is we can actually simplify the problem using what we call an end behavior model, which basically states at infinity, if I just look at the most important parts of it, that's all I need to focus on. Well, what's the most important part of the numerator? It's x squared. What's the most important part of the denominator? It's 2x squared. Well, if I simplify that, what's going to happen to those x squareds?
Cancel.
Those
They
x squareds are going to cancel out, and we're just left with 1/2. Well, what do you think the limit as x goes to infinity is going to be? 1/2. If you remember from prereq stuff, you probably memorized all these rules for finding horizontal asymptotes of rational expressions by comparing, like, if the degree of the numerator is bigger than the degree of the denominator and all those rules. We can throw all those rules out the window using calculus. So like this is one that had the degrees were the same and the horizontal asymptote would be the ratio of the coefficients. Well, the ratio of the coefficients would be 1/2. Well, surprise, that's also what the limit is as x goes to 1/2. And I can adjust that. So if I want to make up a different problem, just to make sure we get it. So if I have, I'll do something similar. The limit as x goes to 2 of x squared minus 3x all over 4x cubed plus 2x. So looking at that example that I just wrote down, let me adjust it so we're actually doing what matters most. So as x goes to infinity. So as x goes to infinity, that tells me I can do what matters most. In the numerator, which term is going to end up mattering the most?
X squared.
X squared.
X squared. What about in the denominator?
4x
cubed.
4x cubed. So we're looking for like the biggest exponent. So at infinity only, or negative infinity, this problem looks like x squared over 4x cubed. Reducing this model, I end up with 1 over 4x. The x squareds kind of cancel out. So looking at this one, I want to kind of again think about infinity. The numerator is still just the number 1, but this denominator is going to keep getting bigger and bigger and bigger. When the denominator gets really, really, really big compared to the numerator, what do we say that limit is going towards?
0.
0. So the limit to this would be 0. Not done with notes yet, but I did want to pause and take questions if I need to go back and clarify anything we've done so far. Because I don't want to lose anyone.
Yeah, I have one.
Mm-hmm.
So, could you just clarify why, when the numerator is larger than the denominator, why it's DNE? Can you just explain?
Because if the numerator is the larger one and it's going out towards infinity, then basically you have like, it ends up being something like infinity divided by a number. And infinity divided by a number, it might be getting smaller, but you're still going towards infinity.
Okay, so the numerator is being divided by a lesser number.
So if I have something like basically a super, super big number, so we have infinity in the numerator, and it could be infinity in the denominator, but it's just much smaller. So like if you just think in your head like really, really big number divided by something smaller, that's still a really, really big number, which in my mind tells me it's going towards infinity. I'll leave you to ponder that though.
Okay.
Try that one though for me, guys. Similar to the other ones, x is going towards infinity. See if you can figure out what that limit is going to be. This will be an example similar to using FEPL and what matters most. So you might use FEPL to figure out which term is going to matter most, and then use what matters most to kind of gives you the option of selecting the terms. So let's look at this one. This is very similar to the other one, but I changed the denominator a little bit. In the numerator, what's going to matter most? The x squared. In the denominator, to help you determine what matters most, is we have a polynomial and we have a log. At infinity, which one of those is going to end up being the bigger one and thus matter more?
Polynomial.
Polynomial.
The polynomial one still. So even though this is a different function from that previous one, it still has the same end behavior model. That's going to reduce to 1/2. So the limit for this one is going to be 1/2 as well. I'm going to do this slide and then stop for the day. And I think that will put us at a good stopping point. So 3 more functions. Again, these are all intuitive. Like I could give you a million problems that are intuitive that are all slightly different. You just have to kind of get used to thinking about it in your head. Having those prereq skills of knowing what these functions look like is definitely useful to you. So let's talk about these. Of these, let's just look at the first one. We can kind of go down. So for the first 2, I do have the limit as x goes to infinity. So let's think about that first one. I have cosine of x all over x. What does the graph of cosine of x look like?
It's oscillating.
It's oscillating, right? So we know it looks like this. What's the biggest and smallest value cosine of x could be?
1 and -1.
1 and -1. So we know it basically is bouncing between 1 and -1. And I can kind of use that idea to help me answer this question. So when I'm thinking about this one, as x goes to infinity, the denominator is the easier part, because as x goes to infinity, the denominator is just x. So I know that this denominator is just going to keep getting bigger and bigger and bigger, like it's going towards infinity. Cosine of x is not part of FEPL because we do know what it looks like. And cosine of x is basically always between -1 and 1. So again, this is kind of all in my head thinking. Cosine is always between -1 and 1, so basically it's always a small number. So I have something small divided by something big. What is the limit for this going to end up being?
0.
0. And so I want you to compare that to the one underneath that. I've added an x plus cosine in it. So cosine is still always between -1 and 1, but now I have multiple terms. So now I get a pick in that numerator. Since I'm going towards infinity, what matters most? Looking in that numerator, and again, you can only pick what matters most if you're going to an infinity. Of course, x in the denominator, what matters most, is the only thing there. In the numerator, what's going to matter most? An x or a cosine? Which one's going to be bigger?
X.
X.
The x, right? So cosine is again stuck between -1 and 1. X can keep getting bigger and bigger. So looking at the end behavior model for this one, what is it going to reduce to?
1.
1. So the limit to this one is now 1. And then this last one I put on here, and this is where I'm going to kind of stop at today. Please don't get used to just always doing what matters most. You can only do what matters most when you're going towards an infinity. For example, if you did what matters most for this problem, you would get 1 again. But since we're not going to infinity, we do want to make sure we plug it in. Cosine of 0 is 1. We get 1 over 0, so the answer would be DNE. And I just threw that one on there to remind us kind of how all of this works. So I'm no means done with kind of these notes. I think you can tell like they're a little bit weird for the most part. And I get that it's not, even though I call it limits intuitively, it's not always intuitive for students to begin with. But tomorrow we'll look at basically just a bunch of other cases to look at. So for your homework tonight, I do want you to go ahead and start its homework number 4. If you're thinking about how the rest of this unit is going to go, so tonight you basically have homework 4, and that's the bell, so I'm done. Sorry guys, we'll pick up tomorrow. I did not mean to take this long today, but we'll pick up tomorrow. Tonight you can go ahead and start homework number 4. By no means finish it, because we do have some more notes to do tomorrow. So I'll see y'all tomorrow. Again, sorry for taking up all of class plus 2 minutes.
Bye, Mr. Brown.
Yeah.
Mr. Brown.